we can use partial fractions to decompose an integral into a simpler form where the degree of the polynomial in the numerator is smaller than that in the denominator. Here we have distinct linear factors in the denominator, so we can rewrite the integrand as follows. Effectively decomposing it into the sum of two constants divided by each separate factor. And now if we multiply through by x minus a by x plus b, we obtain the following expression. And now you can set x equals a to get rid of this term, and that'll give you the following equation. And then you can solve for a, and similarly if you set x is equal to minus b, we get rid of the left term, and we obtain the following equation, which you can solve for the constant b. And now integrating this sum is much easier than integrating this term. In this case, we have a rational polynomial function where the degree of the polynomial in the numerator is smaller than that in the denominator, but we have a repeated linear factor in the denominator. So we can rewrite this integrand as follows. So effectively we decompose the integrand into the sum of a constant on a distinct linear factor, and for the repeated linear factor we have a constant on the power of each factor. So b on x plus b and c on x plus b squared. And now we can follow the same procedure by multiplying through by the factors in the denominator, so we obtain the following expression. Now if we set x is equal to a, well this term disappears and so does this term. So what we're left with is ca is equal to a by a plus b squared. And then we can solve for the constant a, and if we set x equal to minus b, well on the left hand side we get minus cb, and on the right hand side this term disappears, this term disappears, so what we get is c by minus b minus a. And then we can solve for c, and then you can equate the coefficients of x and obtain b. And once we find those constants, this sum is much easier to integrate than this rational polynomial function over here. We have a rational polynomial function where the degree of the polynomial in the numerator is smaller than that in the denominator, but we have an irreducible quadratic factor in the denominator. So we can use partial fractions to simplify the integrand as follows. And for the irreducible quadratic, we write ax plus b on the irreducible quadratic factor. So as you can see, the degree of the polynomial in the numerator is still smaller than that in the denominator. And then for the distinct linear factor, we add another constant on x plus b. And now if you multiply through by the factors in the denominator, we obtain the following expression. And now if you set x equal to minus b, this term disappears, and we end up with the following expression. And you can solve this for c, and you can equate coefficients to obtain the remaining constants. So I'll leave that for you as an exercise. And then integrating this sum is much easier than integrating this rational polynomial function. In this integral, the degree of the polynomial in the numerator is lower than that in the denominator. So we can use partial fractions, and we can try to factorize the polynomial in the denominator. So what we get is x minus 2 and x plus 3. And because we have distinct real factors, we can write the partial fraction as some constant on x minus 2 plus another constant on x plus 3. And if we multiply through by the denominator, well, what we get is 3x plus 2 is equal to a by x plus 3 plus b by x minus 2. And if we set x is equal to 2, then what we get is 5a is equal to 6 plus 2 is 8, so a is equal to 8/5. And similarly, you can also equate coefficients. So the coefficients of x are a plus b is equal to 3, and if you sub for a, you'll get b. And therefore you can write the integral in this form and easily evaluate it. Let's evaluate this integral. So we have the degree of the polynomial in the numerator is lower than the degree of the polynomial in the denominator, and we have a repeated linear factor in the denominator, so we can write the following partial fraction. So a on x plus 1 plus b on the second power of x plus 1. And now we can multiply through by x plus 1 squared, so we get 3x plus 2 is equal to a by x plus 1 plus b. And now we can set x equal to minus 1, so what we get is b is equal to minus 3 plus 2 or minus 1. And if we equate coefficients of x, we get a is equal to 3. And as we can see, the integral becomes much easier to evaluate when it's in this form. Let's evaluate this integral. So the degree of the polynomial in the numerator is smaller than that of the polynomial in the denominator, so we can use partial fractions. And what we have is a repeated linear factor, so we write a on x plus b on x squared, and then plus a distinct linear factor, so we have c on x plus 1. And now if we multiply through by the denominator, we get 3x plus 2 is equal to a by x plus 1 plus b by x plus 1 plus cx squared. And now we can set x equal to minus 1, so that eliminates a and b, so what we get is c is equal to minus 1. And if we set x equal to 0, we eliminate a and c, so what we get is b is equal to 2. And you can obtain c by equating coefficients of x squared, so we have ax squared plus cx squared is equal to 0. So therefore a is equal to minus c or 1. And now the integral becomes much easier to evaluate in this form. Let's evaluate this integral. So we have the degree of the polynomial in the numerator is smaller than the degree of the polynomial in the denominator. And what we have first is an irreducible quadratic. So we write ax plus b over x squared plus 1. And we have a distinct linear factor, so we can write c on x minus 3 as our partial fraction. And then multiplying through by the denominator, we get 3x plus 2 is equal to ax plus b. That's multiplied by x minus 3 plus c by x squared plus 1. And now if we set x equal to 3, we eliminate the first term, so what we get is c multiplied by 10 is equal to 11, so c is equal to 11 on 10. And I'll leave it for you to equate coefficients, and then you'll be able to get a and b, and therefore the integral in this form becomes a lot easier to evaluate. And post your answer in the comments. Let's evaluate this integral. So the degree of the polynomial in the numerator is smaller than that in the denominator, so we can use partial fractions. And we can further factorize the denominator, so we have 3x on x squared by x minus 1 on x plus 1. So what we have is a repeated linear factor. So we're at a on x plus b on x squared. And two distinct linear factors. So we have c on x minus 1 plus d on x plus 1. And now we can multiply through by the denominator. So we get 3x is equal to ax by x minus 1 by x plus 1. And then plus b by x minus 1 by x plus 1. And then plus c by x squared by x plus 1. And then plus d by x squared by x minus 1. And now you can set x is equal to 1, x is equal to minus 1, and equate coefficients. And you'll be able to get these constants, and the integral becomes a lot easier to evaluate in this partial fraction form. And post your answer in the comments.